imagine you have an object like a ball that is thrown and flying through the air. So you can see over here we have a green ball flying through the air. And we're going to neglect air resistance. And when we're studying this object, the only force we have on this ball here is gravity. We have no acceleration in the x direction, and our y direction, the only force we have is gravity. So we can say a of x equals 0, and ay is going to be equal to negative g. So ax equals 0 and ay equals negative g. So since our y-axis shows positive going up and our gravity is pulling down, we're going to write that as a negative number. So how do we find the velocity and the position of the object now that we have an idea of the acceleration? So let's take the acceleration in the y direction, which is equal to negative g, and that is a constant number. So we know that the derivative of velocity with respect to time is the acceleration, dv dt, and thus negative g is going to be equal to this as well. So negative g equals dv dt, and we can rearrange to write negative g dt equals dv. So it's important to remember here too that negative g as a constant equals 32.2 feet per second squared, and it also equals 9.81 meters per second squared. So these are important numbers. You're going to use them all the time. So we can now take the integral of our expression here, so negative g dt, from t1 to t2, and that's going to equal dv v1 v2. Now, simplifying this is going to give us negative g t2 minus t1 equals v2 minus v1. So, if we evaluate at t1 equals 0 by indefinite integral, that's going to give us an even simpler expression. So we'll have negative gt equals v of t plus a constant c. So v of t equals negative gt plus c1. So now we have an expression for velocity. So moving on to position, we know that our velocity is equal to the derivative of position with respect to time. And since we're really just looking at the y direction, we can even write dy dt. So v equals dy dt. And let's rearrange our variables here. So that'll let us write v dt equals dy, and we're going to integrate. So v dt equals dy, and let's plug in what we know for v. So let's write negative gt plus c1 dt equals dy. And that's going to give us an expression for y of t equals negative 1/2 gt squared plus c1 t plus a constant c2. And these constants are going to be evaluated from the initial conditions. So at y0 equals y0, so when the time equals 0, we're going to write y subscript 0. And our velocity in the y direction at time 0 is going to be vy subscript 0. So those are just our initial conditions. So we can even write that as y of t equals -1/2 gt squared plus vy0 of t plus y of 0. So that is our final equation for y of t that we are going to have. So to summarize, let's clear some of our space here. We're going to have an x set of equations and a y set of equations for these types of problems. So let's see. So in the x direction, we know that ax equals 0, and we know our velocity in the x is going to be equal to our initial velocity. And our x position is going to be equal to that initial velocity times time plus our starting position. So this is good for when the when the acceleration in the x direction is equal to 0, that these other two equations here apply. And now for the y direction, we can say that ay is going to be equal to our -g constant, or really any other constant. Our vy is going to be equal to -gt plus vy subscript 0. And our y position is going to be equal to -1/2 g of t squared plus vy0 t plus y subscript 0. And this is good for any time that the acceleration is constant. So here we have -g, but again, it could be anything. It could be -5 meters per second squared. So as long as it's a constant acceleration, this set of expressions are good. And as long as for the x, we have a acceleration in the x of 0, these set of expressions are good. So another important thing to discuss that'll come up is, what is weight? So weight is simply the mass times the gravity. So a lot of times they will, just ask this as an aside question, but it's important to know. And whatever system you're using, if they're giving you, if the problem is in English units or in standard units, you want to make sure that you're using the right number here for G. So either 9.81 or 32 feet per second squared. So now, what if they give you acceleration as a function of velocity? So that would look like a is going to be equal to a function v with respect to v. So we know that a equals v dv ds from our previous videos. And so we can say a of v equals v dv ds. Now that expression is pretty powerful because that lets us write a of v equals v dv ds to integrate ds equals v over a of v dv. So that gets all of our variables on the right side, and that will let us evaluate and integrate both sides respectively. On the left, we're going to be integrating with respect to s, and on the right, we're going to be integrating with respect to v. So that will give us an expression for the position as a function of velocity. And if we're given acceleration as a function of the position, we can solve that by saying a of s equals, again, v dv ds. And that'll let us integrate both sides again by rearranging our variables. So a of s ds equals v dv. And we can use the same expression here to just integrate, and the left side will give us an expression with respect to s, and the right side will give us an expression with respect to v. And that's going to continue letting us solve through these problems. So in the next video, we'll do an example of projectile motion, but this is just an overview and showing you the equations that are applicable to projectile motion and how we can manipulate these variables to give us what we are asked for.
Thank you for watching. If you like this video, please be sure to give it a thumbs up and subscribe. That really helps support my channel and helps me continue making videos for you guys. I'll see you next time.